Measuring acidity. Very common measurement. I mean, it's almost, sometimes it's after the fact, though. I mean, all the little fishies are dead, and they measure the pH, and it's just way too acidic for them. So that's probably why places like San Antonio River Authority and very common environmental measurements is they have probes all over throughout the rivers and lakes, and they're monitoring acidity, they're monitoring oxygen levels, they're monitoring a lot of different things. So I think pH is more of a monitoring thing than it is, you know, after the fact. But any commercial process like brewing beer or making any chemical product, they're going to be monitoring pH the whole way along because they know what it should be to get the right answer, to get the right product, to get the best product. So if they start getting off track, I think pH would be a good little warning signal. In your own body, you get acidic, and it shows what happens. You get tired, start getting tired, but between where cells die and cancer, you know, they're not so sure. That's an area of research there, but it's very useful. We have a pH scale, and Daisy, if the solution is neutral, the pH is supposed to be what number? Someone said it. 7. And if it's acidic, then the pH is supposed to be, yeah, a number less than 7. If it's basic, then the pH is supposed to be bigger than 7. All right, more than 7. Okay. Oh, before we move on here, this is what in lab this week, you're going to use this to measure pH, a pH meter. And along the table here are a whole bunch of buffers, and they say pH 10, 4, and 7. And a buffer, we'll talk about that, what a buffer is in upcoming class periods, but essentially just the solution that maintains the exact same pH, or something really, really close. And it's really good at resisting changes in pH. Your blood, for example, is buffered. Anyway, right now the pH meter is reading, what does that say, Erica? 6.99. And it should say something really close because it's in the pH 7 buffer. Now, do you remember when we talked about, how about this pure water? This isn't pure water. I got this from the tap. Jessica, what do you guess its pH would be? Around 7. So I'll put it in there, and I'm stirring it. We'll talk about that in lab, why that's a big deal. And it looks like, what, Albert? So that's acidic or basic? That's acidic, right? What the heck would be in tap water to make it acidic? You know there's a lot of minerals and stuff. You can see them caked around the faucet here. Now, they put chlorine in there to disinfect, right, to keep people from getting sick and things. To me, what I think is the acidic thing, now you can't really answer copper or calcium or iron. That's not going to have any effect on acidity. But what will is stuff like carbonate and bicarbonate, but we'll talk about that later, right? I think for now, what the answer pretty much can be, one of the big reasons why this soda was acidic. Pop this soda can open and you hear the what gas is that again? Carbon dioxide. Carbon dioxide dissolved in water turns into carbonic acid. So it's an acid. So I think there's a lot of CO2 dissolved in tap water. That's a big reason why it's acidic too. I think Albert said 6 point something of it. So it's acidic, but not really acidic. How about the Pepsi, though? Sochi. Remember those pictures of the teeth? That poor dude wasn't brushing his teeth after drinking all this soda, right? I put the little pH meter in the soda. What do you think it's going to read? What would you guess? Yeah, but what number, though? That's 4. All right. I'm like a reasonable number. I don't know, Daisy, what does it say? I can't read it. 2 2.07. So that sounds really, really acidic. You want to be brushing your teeth after this. Okay, after you drink soda. Okay. Think it would matter much if it was diet soda? I don't think so. That'd be a good test, though. All right, see if it really is the carbonation and phosphoric acid and things that are doing the trick. Okay. Now we have some equations that are going to help us out with pH. And pH is the negative log of brackets H. Jessica, what do you think these brackets mean? We had them before. We wrote them before in equilibrium concentration. Good. For this, all this to work, though, Grace, concentration needs to be in a certain set of units. What units should you be picking? Big M, which is what over what again? Moles over liters. So big M is a lot easier to write. Exactly. So we have pH is the negative log of hydrogen ion concentration. POH is the negative log of hydroxide concentration. Then we have POH. Okay. Let's play around with this a little bit, because it's the calculators that I think that are going to give us the trouble here, Kathleen. If the hydrogen ion concentration is 3.8 times 10 to the negative 3, what is... So, I don't know how I can ask that a question. Whoop. Okay. pH is negative log. I can't really make that a question. You have to plug it into the calculator. I can ask Kathleen what she got, though. All right. 3.8 10 to the negative 3. So 3.10 to the negative 3, then you got to push the log button. And then at the negative sign, what did you get? She got 2.42. That's what I got, too. So you should be getting 2.42 when you're doing everything right so far. No troubles there. Now we've got pH is 2.85. What is the hydrogen ion concentration? So if pH is negative log of H, concentration. Now they tell us the pH is 2.85. What is the hydrogen ion concentration? We need to get rid of that log. We need the inverse function of it and do that inverse function to both sides. What was that inverse function? What was it? Raise both sides to what power? Okay, now there's little e, and the other choice was 10. This is a very common thing. It's little e. If we're not using log, logarithm, we're using little l, little n, natural log. That little e number is everywhere in nature, so they give it its own natural log. Log is base 10. So we have to raise both sides to the 10 power. And that's how let's show all this. You bring the negative sign over first. Then you can see what's going on here. Now you raise both sides to the 10 power. Now what cancels? I mean, it's kind of like saying x times 1 over x. You just get 1. The 10 and the log part, yeah, it goes away. So what we end up with is 10 to the negative pH is the hydrogen ion concentration. So we just have to take 10 to the negative 2.85, and we should get our answer. Okay? So I would put in 2.85 first, make it negative, the plus minus button, and look on there for the right button here. I need, oh, there's a 10 to the x, right? In my calculator, it's shift 10 to the x. I get 1.41 times 10 to the negative 3. Okay? So raise 10 to the negative 2.85 power. Okay. Or I guess another way to do it is there's an x to the y button. You could push in 10, then push the x to the y. What power do you want to raise it to? 2.85. And do it that way too. Okay. Any trouble with that? Juan, you got it? Okay. So there's our answer. Now you go through all that calculator, you do it all right, and I still take a point off. Just in a bad mood, Erica, or what? You got to put the big M, or write moles over liters, right? Okay. One thing I want you to notice is up on top, these are all the equations I give you, right? All of those. 10 to the negative pH is hydrogen ion concentration is realize how to get it. Okay? Okay, so 10 to the negative pH is hydroxide. That's not given. You just have to realize, oh, I got it from there. Okay? Likewise, you could say 10 to the negative POH is what concentration? From this one. 10 to the negative POH is what? If pH was 10 to the negative, if 10 to the negative pH is, what the heck am I doing here? Right? All right. 10 to the negative pH is hydrogen ion concentration. 10 to the negative POH would be hydroxide. Right. Okay. All righty. How about this bottom one? You've got pH is 8.35. What's the hydroxide concentration? I changed a few of these on your handout. If the pH 3.5, what's the hydroxide concentration? What's that? I don't know. I just made up the question. It might be. Oh, if we take the pH, you subtract the 8.35 from 14? Okay, so what you subtract is 8.35 from 14. She used this one. What pH plus POH is 14. And so this is 8.35. Just to show you. So that POH to be, what was the number? 5.65. Now the P, she's really, really close. But the POH isn't hydroxide concentration. It's POH. So there's one more step. But she got the first step right. You see that? So first she found POH, and now we got to find. Now we can find hydroxide. All right? So we know that POH is a negative log. And then you got to remember, oh yeah, that means if I raise both sides to the 10 power, get out of there. 10 to the negative POH is my hydroxide. Okay. So I have to take 10 to the negative 5.65. Then I'll get it. Okay, 5.65. Make it negative, 10 to that power, 2.24 times 10 to the negative 6. Big M. Okay. You see that? So they told us pH, they want to know hydroxide. So you just sit up here and look at all these equations. They want to know hydroxide concentration. Well, the only place it shows up is here. Well, that means we got to find POH. How do you first? And then find it. Okay. There's always an equilibrium between water and its ions, and you just can't stop it. I mean, water just, they call it autoprotolysis, self-ionization. Water decomposes. You just can't stop it from happening. And in your notes, what ions does water break up into? And you have it written down. And OH minus. You can't stop it from happening. Valerie, what would you say the equilibrium constant expression is? K is what? H plus concentration and OH over H2O, but it's a pure liquid, so we don't put it in there. And actually, you could write it in there, but it's 55.4 molar. So it's just a number. They're going to include all these constants with the equilibrium constant. So it's not there. So I guess you could write over 1 or something. Okay. Common equilibrium constant expression. And they're going to give it a W. Probably the W is for what? Water. Yeah. Do you think that number is really big or really small? That KW. Let me find it, but what do you think? K equilibrium constant expressions are products over reactants. So what are you going to have a lot more of? Are you going to have a lot more of the products, or a lot more of the reactants, or equal amount? Here's water. It's almost all which form? You have H2O liquid, or H plus, or OH minus to pick from. It's all pretty much in the, I can throw it on you. It's on the wet form, right? It's all in the wet form. Hardly any of it breaks up. Hey, what it does, you can't stop it. So it's a really small number. It's 1 times 10 to the negative 14. Okay? And that's another equation that they're going to be giving us. Or I'll be giving you on the homework and stuff. On the equation sheet. W is hydrogen ion concentration times hydroxide, and it's always that number, 1 times 10 to the negative 14. How can I change that number? Only doing one thing. Change the temperature, right? So if they change the temp on you, they're going to give you a different number. But that's just room temp. Okay. Small number. Negative 14. Solutions of strong acids and bases. We're going to start getting into calculating pHs of solutions and strong acids and bases. But Jessica, you really don't need to memorize all these strong acids because they're all on this. They're on that table. Where do you look to see them on the table? Yeah, the top, strongest acids, the top 6. They're all there. We just look at the table to see those. However, the bases, to know if something's a strong base, I don't know. I think the only way to know it is to remember the solubility rule. And you go by hydroxide. Because hydroxides are base. What can you put with hydroxide and make it completely dissolve? It doesn't. It's a strong base. Now, you can get a bunch of them just by remembering, I think it was solubility rule number 1. These ions, you put them with anything, it always dissolves, 100%. What were those ions? You remember? Group 1, sodium hydroxide, lithium hydroxide, potassium hydroxide. Man, You see these, you know they're strong bases. And then you pretty much have to use Google and go back and see what. There's also some exceptions. The hydroxide forms precipitates all the time. Lead hydroxide, silver hydroxide, all precipitates. Except for with these, group 1, and then there were some exceptions to the rule. There was calcium hydroxide and barium hydroxide. I don't think you're going to see any homework on them, but just in case you do, those are 2 more strong bases. Not very common, though. Okay. So why do we do that? Because these are the only types of compounds we can work with right now in calculating pH of. And that's strong acids and strong bases. Because they dissociate 100%. So let's see what the big deal is there. Here's our equations. Calculations of solutions. Trying to get at pH, POH. We have 0.25 molar HCl, Mariella. What's so special about HCl? Yeah, what type of acid? It's strong acid. And that's pretty much the only type of acid and base all these questions can deal with right now. It's a strong acid. It's on the list, top 6. It's supposed to dissociate what percent? 100%. Does anyone know what the answer is right off the bat, though? Nobody? Okay. HCl, 100%. H plus and Cl minus. Exactly. Okay. If I had 1 HCl molecule, how many H pluses would I get? 1. If I had 10 HCl molecules, I'm going to get 10 hydrogen ions. If I have 0.25 molar HCl, I'm going to get 0.25 molar H plus. It all breaks up. Okay, 0.25 molar. It's a strong acid. What's so special about NaOH, Erica? Strong base. Okay. So Erica, Valerie, what would be the concentration of hydroxide in 0.15 molar sodium hydroxide? Erica gave us a hint. Strong base. Hydroxide concentration has to be the 0.15. The exact same thing. So it breaks up 100%. You can dissociate. In fact, you could even say, what's the concentration of sodium ion? What is it? 0.15. Right? It all breaks up. Okay. Okay. But if they were all that easy, that would be nice, but they're not. What is the hydrogen ion concentration in 0.15 molar NaOH? Okay. Now we've got some calculating to do, because all we know is what? Not the hydrogen ion concentration, but hydroxide. We know this. We know the hydroxide concentration is 0.15 molar. Then you got to look up on all those equations up on top. How can you get at hydrogen ion concentration? Okay, I heard someone talk about this one. Let's make this a different color here. We could mess with this one. Can we? Oh, we can't even mess with that one because we don't know POH. We just know hydroxide concentration. That won't work. OKW. Yeah. Use that one because then we know hydroxide. We can solve for hydrogen ion. Yeah. 1 times 10 to the negative 14 is hydrogen ion hydroxide. So 1 times 10 to the negative 14 is hydrogen ion The hydroxide concentration is 0.15 molar. So we'll just divide both sides by 0.15. So divide by both sides with 0.15 and you get the sign of the devil, right? 6.67 and 10 to the negative 14 hydrogen ions. Okay. Juan's way was the fastest way to skin the cat, fastest way to get the answer. Do you see a much more complicated way? Now, it would have worked. Yeah, Daisy said it. A much more difficult way is make this red or something. You don't want to do it this way, but you could. You could do this one first, right? And then you got PO8. Then you could probably use what? The 14. Use this one to get pH, and then use this one to get the H. Right? That would work. That would work. You get the exact same answer. Okay? So there's easy ways and hard ways to work these out. What is the pH of 0.05 molar NaOH? At 0.05 molar NaOH, we want to know what the pH is. Yeah, what's the pH of that solution? What could we do first? What do we know? Start with what you know. We know the concentration of what? OH. Let's write that down. That's our starting point. We know that this is what, everybody? 0.05 molar. What you know, that's your starting point. So what could we do with it? Use the second one. That would be a good idea. You don't have to do it this way, but this way will work. Use this one to get POH. If you did this one first, and then second, the 14 is pH minus POH. Work? Try it. First find POH, and then subtract from 14. I got about 12.7. So first we on the POH, then we subtract from 14 to get the pH. Okay. Well, there's another way to do this one. If we knew the hydroxide, instead of doing it that way, I bet there's another way, right? We could have done what first? Yeah, use the KW. This is important to see because you can see more. If you can see this, you're really on track here. Use the KW. And then from that one, we get the hydrogen ion concentration. And then you'd use what? pH. Right? There's another way. If you can see that, you're really, this isn't going to give you too much. Okay. What do we have here? What are the concentrations of the hydronium ion and the hydroxide in each of the following? So Jessica, where's this hydronium ion thing coming from? That's just what? Instead of writing H3O plus, we could just write what instead? Want to remember? H plus. It was just H plus. So if that looks ugly to you, just cross it out and write H plus. It's the exact same thing. Okay? They want to know both. Their concentrations. So Grace, one's easy, one's more work. What's the easy one? H plus. In fact, it's going to be exactly what? 1.2. She got the easy one. That one's done. Now we got to find the hydroxide. Kathleen, you have an idea? Yeah, concentration. Do the what? It's got to be one of this. Oh, she's talking about this KW one. I think so too, because you know what one is, you can find the other. Okay. 1 times 10 to the negative 14 has to be 1.2 times their hydroxide concentration. And we'll have it. About 8.3 times 10 to the negative 15. Okay. I changed the order of the questions. This one next. I think this is as complicated as it's going to get. And if we can handle this one, I think we're going to be able to handle the homework all right. They say that a detergent, like these soap solutions, very often they're basic, and it's pH of 11.63 at 25 degrees Celsius. What is the hydroxide ion concentration? They give us pH. We want to know hydroxide ion concentration. Anybody have a game plan? Okay, we could use 14 equals pH plus POH to get us what? The POH. That'd be a nice one. And then we don't have hydroxide ion concentration. We have POH, though. Then how do you get hydroxide ion concentration from POH? Solve for that hydroxide concentration. See if you remember how. I think Mariella gave you a good start on that. I would use 14 as pH plus POH first. Okay. Now, another way to get the hydrogen ion concentration, and then use the KW expression to get hydroxide. That would work too. I see two ways. Okay. But both of those should work. Get an answer? 4.27 times 10 to the negative 3. Okay, 2 people got that. Final answer. See if you can get that. Juan, you got it? Well, if you got it and your folks around you got it, go on to the next one. I'm going to make sure everyone can see this. The negative sign's gone now. Yeah, you brought it over. Because you brought it over there. So it's the negative. Now your 10 and the log cancel out, and you'll have it. So 10 to the negative 2.37. So go on to the next one if you got it. Oh, man, that's nice. I think you should like problems like 63. Not much. 63, though. Yeah. Or acidic. Just write acidic, basic, or neutral next to each one. So in 67, hopefully you realize hydronium ion, remember what that is, that's just H+. Hydroxide, that's the OH- in 71. A couple minutes left. Yeah. Oh, this is, for the pH. So 10 to the negative pH would be H. Well, no, I mean, just if you want to, there's no real, on this one you can just write pH is 14 minus POH or something. There's no, yeah. Yeah, just for those. So have a good day.